Hi everyone, welcome back to Engineering Simplified. For the past few videos, we have been talking about forward kinematics. So I thought this would be a good time for me to show you exactly how do we implement forward kinematics using Matlab. I am going to be using Matlab for the purpose of this video, but you can do the same using Python, C++, or any programming language that you are comfortable in. So just a quick review, what is forward kinematics? Forward kinematics is when you are given the robot parameters and you have to find out the end effector location and orientation. So for this video, we are going to be talking about this robot, which is a 6 degrees of freedom robot. And we are going to be first doing the forward kinematics of this using pen and paper approach. Then we are going to transfer it into Matlab and I'm going to show you how that is done and the results that you get out of it and how to interpret those results. So stay tuned and let's start with that. So let me first dissect this robot a bit. So we can see that at the base of the robot there is one joint right here, which is at the bottom, which is a revolute joint. So it can rotate about the base. I can call this theta 1 maybe. Then there is another revolute joint right here. I can call this maybe theta 2. Then there is another revolute joint right here. So I can call this theta 3. So these are the three revolute joints. Then right here you can see there is another joint. I don't know exactly if this is a revolute joint or a prismatic joint, but for this video and to make sure that I covered both prismatic and revolute joints, I am going to assume that this is a prismatic joint. So what that means is the robot can extend and contract in this direction. So it can basically extend and it can contract in this direction. I can maybe call this A4 since this length is going to be changing throughout. So I can make this extend or contract. And then right here, you can see that it can first rotate about this direction, which is the revolute joint. I can call this theta 5. And then right here, it can revolve around this direction as well. I hope that makes sense. So it can first rotate about this direction and then it can revolve about this direction. So theta 6. So now we can see that the parameters of interest, which are robot parameters, are theta 1, theta 2, theta 3, A4, theta 5, theta 6. Since there are 6 parameters which define the end effector location and orientation, hence we call this robot a 6 degrees of freedom robot. Right? 6 degrees of freedom because there are 6 independent parameters that can be controlled. So the first step whenever you want to do forward kinematics of any robot is to first draw out a schematic of the robot. That will kind of give you an idea of how the robot is behaving. So I'm just going to draw a very simple schematic right here, just to give you a very good idea of how I'm going to be doing the forward kinematics of this robot. So at the base there is a revolute joint. I can just draw a cylinder to represent a revolute joint. Then there is this part, and then there is another revolute joint, right, which is in this direction, and then there is this part right here, and then there is another revolute joint, and then there is this, and then I can call this as a prismatic joint. So this I can represent it as this is a prismatic joint. And then at this point there are two revolute joints. The first is in this direction and the second is about this direction. Let me redraw this. So I can say that the first is in this direction and the second is in this direction. And then from here to the end effector base here there is a set distance. So I can just say that this is the distance, and right here is my end effector tip, which is this point. So let me just mark this out. So let me say that this right here is my end effector tip, or I just call this my end effector. Now before I begin, I'm just going to mark out the fixed axis of the robot. So let me mark those out. So what I'm going to assume is I'm going to assume that this direction is the x-axis. Into the plane is my y-axis, and going upwards is my z-axis. Okay, hope that makes sense. So x is to the right, z is going up, y is into the plane. Now I have to do the forward kinematics of this robot. So we are going to go step by step, and we are going to start from the base of the robot and go to the end effector and do the forward kinematics using homogeneous transforms. But before I do that, I just want to mark out a few things on my schematic. So what I'm going to do is I'm going to assume a few things. So first and foremost, so what I'm going to do is I'm going to assume that for this length right here, there's going to be some x direction and a y direction component, right? So I can just mark this out. This is x and z direction component. So I can mark this out as something and something. I'm just going to be calling them as x1 and z1. And similarly, once I go from this point to this point, there's going to be some minus x direction component and some z direction component here, and then moving forward, right? So so let me start out doing the forward kinematics. So first and foremost, I am going to be writing the first homogeneous transform. So my first homogeneous transform, which is going to be by h1, is simply going to be a rotation about the z-axis, which is this one, theta 1. So z of theta 1, and there's going to be no displacement in my first homogeneous transform, since it is just a rotation about this point, no displacement. So there are going to be 3 zeros here, and then my bottom row is always 3 zeros and a 1. So this becomes my first homogeneous transform. I can just call it this h1. Now my second homogeneous transform, which is going to first take this point and move it right up to the center of this revolute joint. So in order to go from here to here, there is going to be some displacement in the x direction and some displacement in the z direction. I can just call this as x1 and z1. x1, z1, and there's no displacement in y, so 0 and z1. And my last row is always 3 zeros and 1. Now remember that if you have a real robot with you, these x1 and z1 are going to be fixed parameters, right? So it is going to be known. So when I'm going to be doing the coding for this, I'm just going to assume values for x1 and z1. So now what this does is it takes this point right here and translates it to this point. Now there is going to be a rotation involved, which is going to be in the y direction, which is into the plane. So there is going to be a rotation of y by theta 2, right? So the first rotation was about z axis right here, which was theta 1, and my second rotation is about this axis, which is theta 2 right here. And remember that we are using the right hand rule. So counterclockwise direction is taken to be positive. So we have got our first homogeneous transform and our second homogeneous transform. Now to get a third homogeneous transform, what we first need to do is we first need to go from this point right here to this point. So we have to go from this point right here to this point, which is obviously going to involve our displacement. So the displacement that there is going to be some displacement in the minus x direction I can just call this minus x2. And then there is going to be no displacement in y, and then there is going to be this positive displacement in z direction. I can call this z2, 1 0 0 1. So now I am at this point, and now at this point there is going to be a rotation involved, which is going to be about the y-axis. So this rotation about the y-axis, which is going to be theta 3. So I can call this y of theta 3. So now I have my third homogeneous transform here. Now moving forward is there is going to be a prismatic joint. So to go from here to this point right here, or from going from here to here, there's first going to be a displacement involved. So for this displacement, I know that this displacement is going to be due to the prismatic joint, which is due to A4, right? So A4 in the x direction. Now remember that A4 is variable. It is not fixed for the robot, but it can move as desired. So this is A4, which takes, let me mark out A4 so there is no confusion. A4 goes from, okay, if I mark this out right here, so A4 goes from here to here. So there is going to be a displacement by A4 in the x direction, no displacement in y, no displacement in z. Then there are 3 zeros in the bottom row and a 1. And once I get to this point, right? So once I get to this point, now I can see that first there is a rotation about the y-axis, which is theta 5. I am talking about this one. So first there is a displacement about the y-axis theta 5, and then there is a displacement about the x-axis, which is theta 6. So I can combine those two out, and I can write first there is a displacement by y, which is theta 5, and then there is a displacement by x, which is theta 6. So here, so what I have done in my fourth homogeneous transform is first I have displaced it from uh, I have displaced it from this point to this point. So first there is a displacement which is given by a4 in x, 0 in y, and 0 in z. And then once I reach this point right here, I first rotated by theta 5 around the y-axis, which is going to be this theta 5. And then I rotated about the x-axis, so which is going to be about this, which is theta 6. And why have I done it first in y and then in x? It is because of how the robot is constructed. We can see here that first it is going to be rotating about theta 5 if I go from the base towards the end effector. So first there is a rotation about the y-axis, and then there is a rotation about the x-axis. And once I have done that, I can see that once I am at this red point, and if I need to go towards the end effector, there has to be another displacement, right? So I need another homogeneous transform, but this time there's going to be no rotation whatsoever. So there's just going to be an identity matrix right here. And for the displacement, there is going to be some displacement. I can call this x3, which again is fixed, which is just distance from here to here, which is x3. Then there is 0 in y, 0 in z, 1 0 0 0. And this is my fifth homogeneous transform. So if I multiply h1, h2, h3, h4, h5, what I get is the location of the end effector and its orientation in the fixed frame. So what I get is I get the location and orientation of this point right here, which is the end effector. So I get the location and orientation of this point right here in the fixed frame. And what is my fixed frame? My fixed frame is the one which is fixed at the base, which is this x going up z and going into the plane y. And one thing that I forgot to mention beforehand is that whenever you are doing the forward kinematics, you do the forward kinematics at the zero configuration of the robot. What I mean to say as the zero configuration or the home configuration, let me write it out. So the zero configuration, zero configuration, or also known as the home configuration. So home configuration. So what that is when we assume that all the robot parameters are at 0 degrees or zero lengths, right? That is what we assume. So they are at their initial position. So we assume the robot is at its zero configuration, and we do the forward kinematics of the robot at its zero configuration. And then whenever we change any parameter, it is going to be changed from that position onward. So what I mean by this is, if I do the forward kinematics in the way that I have done it right here, so what I have taken is, I've taken that the robot, the link of the robot right here is horizontal, right? So now this is going to be the case for my forward kinematics. Now when I change my theta 3, so theta 3 is this one right here. So when I, let's say when I make theta 3 go to be 20 degrees, so what would happen is my robot, this thing would go down, right? Because my theta, I've taken theta 3 in this direction, which is counterclockwise, right? So it would go down, and this is 20 degrees, let's say. So it is positive 20 degrees would go down. And similarly, if I make my theta 3 to be minus 20 degrees, this would go up. So this would be my minus 20 degrees. Why? Because theta 3 is again counterclockwise. So remember that we are always using the right hand rule. So all angles are taken to be positive when counterclockwise. Okay. So I have got this. I have done the forward kinematics, and this is literally all there is to it. And if you don't remember, so what the rotations are these. So x rotation is simply this matrix, y rotation is this matrix, and z rotation is this matrix. And now what we need to do in Matlab, or if you are doing it in Python or C++, so what we would need to do is, we would need to write out these homogeneous transforms separately, multiply them out, and then whenever we want to know the forward kinematics of the robot at any particular robot parameters, we just are going to replace the values of theta 1, theta 2, theta 3, theta 4, sorry, theta 1, theta 2, theta 3, a4, theta 5, theta 6. We input those values, and we are going to get one homogeneous transform, which not only shows us the robot end-effector's location, but also its orientation. So let me just do all of that in Matlab. So let me open Matlab right real quick. Let me put this on one side. So right here I have my Matlab open, and I am going to be working in a live script. So new live script, and I'm first going to give a few initial commands. Clear all, close all. Now first and foremost, what I would do is, I would define a variable which I'm going to call theta. Okay, first I am going to, and now I'm going to write out the three rotations: x rotation, y rotation, and z rotation. So x rotation, which if you don't remember, is this one right here, x rotation. So x rotation is a 3 cross 3 matrix which has a 1, 0, and a 0 in the first row. Then there is a 0, then there is a cosine of theta, and then there is a minus sine of theta, and then in the third row there is a 0, there is a sine of theta, and then there is a cosine of theta. And now y rotation. Y rotation is again a 3 cross 3 matrix which has a cosine of theta. Then there is a 0. Then there is a sine of theta. in the next row there is a 0 1 0, and then there is a minus sign of theta, there is a 0, and then there is a cosine of theta. Don't worry, we just need to do it once, and then I can just substitute the values for these. And then there is a z rotation, which is going to be cosine of theta minus sine of theta 0, and the second row is sine of theta cosine of theta, and then there is 0, and the third row is 0 0 1. Let me just run it out and we can see the result on the right side. Okay, so yes, I think I made a mistake.
Narrator dialog. Matlab R20 narrator heading level 1 jump list exiting narrator.
Okay. Yep. So on the right, I can see that this is X rotation, Y rotation, Z rotation. Let me just quickly confirm that I have not made a typo. So this looks to be correct. Yep, it looks to be correct. So now what I am going to do is I'm going to write out my homogeneous transform. So H1, which is this one right here, is the rotation about the z axis by theta 1, and then there is no displacement, right? So first I can just write there is, I can just substitute. So before that I can define a few other variables. I can define theta 1, theta 2, theta 3, theta 4. Sorry, there is a4, theta 5, and theta 6. And then remember that we had values for x1, x2, z1, z2, and those. So I'm going to define specific values for those. So I'm going to keep x1 as, let's say, 1, and x2 as 2, and x3 as 2 again, probably. Let's say x3 x.5, and then there was a z1, which I can call this as 2, and then there was a z2, which I can say is probably 1.5. Okay, so I am just talking about these variables right here. So this these variables. Okay, so now my first homogeneous transform had a rotation about the z, so I can just write out, I can just substitute in the z rotation matrix. In place of theta, I can just write theta 1. So you see, I just need to write out x, y, z rotation once, and I just substitute those values, and then there is a displacement of 0 0 and 0, and then my last row is always going to be 0 0 0 and 1. And now I can just check it out too. So this h1 is my first homogeneous transform. Similarly, I can write out h2, or I can just probably I can just copy it out too. It should be, I can just make changes. So h2 was a y rotation by theta 2, and in the displacement there was x1 displacement in x, 0 in y, and z1 in z. So again, let me bring this up. So I'm talking about this one right here. So x1 0 z1, and rotation about y by theta 2. So this becomes my h2, and similarly my h3, let me just copy this again. h3 was a rotation about y by theta 3, and there was a displacement by minus x2, 0, and z2, and my h4 was, it consisted of a displacement by a4, 0, 0. Now remember that A4 is one of my prismatic joint. So the value of A4 can change. So A4 0, 0, and there were uh, two rotations involved. The first was about the y-axis by theta 5, and this was followed by a rotation about the x-axis by theta 6. Theta 6. And then there was this last homogeneous transform, which is my h5, which just had a identity matrix at the start, so there was no rotation involved. So I3, which is my identity matrix, and the displacement was x3, 0 and 0. Now on the right we can see all the homogeneous transforms. So there is h1, h2, h3, h4, h5, right? And now to get the forward kinematics, fk forward kinematics, I just multiply h1 by h2 by h3 by h3 by h4 by h5. So I'm just going to write semicolon after this so they don't show up on the right. And now when I run this, I'm just going to see the forward kinematics, which is going to be a big matrix. So this is my forward kinematics. Okay, so this is a forward kinematics. What it is it is a 4 cross 4 matrix, and since it is a homogeneous transform, so I can expect that my bottom row would be 0, 0, 0 and a 1, right? So, and then there is going to be a 3 cross 3 rotation matrix in on the top left, and on the right side there is going to be a 3 cross 1 matrix which shows me the position of the end effector. Let me just quickly tell you what I mean by that. So what I did was, in this what I did was I wrote out the homogeneous transform h1 through h5 and I multiplied them out, and what I got was a forward kinematic, this one, fk, which I called fk in my code, or I can just simply write as h. And what I am going to get is I'm going to get a homogeneous transform which is going to be of the normal form, homogeneous transform. So it is going to have 3 zeros and a 1 at the end. And then on this side there is going to be a 3 cross 1 matrix. So 3 rows and 1 column, and what that would show me is the position of the end effector in the fixed frame. So it is going to show me the position of the end effector in the fixed frame. So it is going to show me the xyz coordinates of the end effector in the fixed frame. And then here I am going to get a 3 cross 3 matrix, which is going to be a 3 cross 3 matrix. What that would show me is the orientation of the end effector in the fixed frame. So if I talk about the orientation in the position that I have drawn right now, so right here, what I've taken is I've taken that at the end effector, my x-axis is going to be orienting this way, my z-axis is going to be orienting this way, and my y-axis is going to be orienting into the plane, right? This is the orientation. Now this 3 cross 3 matrix is going to show me exactly how this orientation would change with changes in the robot parameters. So how do we make use of this? So now what I've done is I have figured out my homogeneous transform, I have figured out the forward kinematics, and I have got one single matrix which is a 4 cross 4 matrix which has got all these mumbo jumbo involved, which has got all these theta 1 through I would say theta 6 including a a4. Now let's say someone comes up to me and he gives me specific values for these theta. Let's say he comes up to me and he says that, let's say the theta 1 is 20 degrees, so 20 over 180 into pi, because I am working in radians. He comes up to me and he says, okay, your theta 1 is this, your theta 2 is, let's say, 10 degrees, your theta 3 is, let's say, 5 degrees, and he tells me your A4 is probably 3 meters, your theta 5, sorry, this is theta 3, this is theta 5. He comes up to me and he says your theta 5 is 30 degrees, and your theta 6 is, let's say, minus 20 degrees. Okay, so he has given me all these robot parameters. So he comes up to me and he says, okay, you have the robot right here, and I want you to make the robot achieve these values of theta 1, theta 2, theta 3, A4, theta 5, and theta 6. So now all you would do is you would go into the software of the robot, input these values, and it would make the robot go and achieve those values, and you would see the robot moving and it would achieve a specific orientation and position. Now what you need to figure out right now is, if you input these values, what would be the location and orientation of the robot. So you would do this before you give the command to the robot to actually move. So you do this and you see how the robot would actually move and where it would be in space, and then if everything looks right, you would actually go and give the command to the robot. So what I would do is, I have a forward kinematics command. I would just go about and I would just substitute the values. So in forward kinematics, for theta 1, theta 2, theta 3, A4, theta 5, and theta 6, I can just substitute T1, T2, T3, T4, sorry, A4, T5, and T6. And now when I run this, I can just call it this forward kinematics with values. So now when I run this, I am going to get a 4 cross 4 matrix, which is going to be a homogeneous transform. So yeah, so I get a 4 cross 4 matrix which has got all the unsimplified form. So I can just write simplify it and write double probably, and maybe I can even use a VPA just to make things a little easier. VPA, and okay, so 3. Okay, there is some issue with the code. Okay, so substitute. So once I substitute that, I think I made a mistake. Let me just quickly go and correct that out. So I remove the VPA from here. I probably should remove these terms right here. Now let me run it out. I know it is taking a bit of a time, but the thing is, you only do the forward kinematics once, and then once you have the results, you just substitute the values, and you get the answer. Okay, so there is some issue with my code. Let me just see where the issue is. So this should be okay. Okay, so substituting this should give me this. Okay. Okay, does this work? Then still waiting for the answer. Sometimes it can take a bit long, and now right now, since I am recording and stuff, I have a lot of softwares running, so it is taking a bit of time. So I've got an answer, and I can see all of these are just numbers, so I should probably be able to VBA it and see if that works. VBA by 3, maybe, hopefully it works. So I'm keeping my fingers crossed. Okay, yeah. So now it works. And did I not define A4? Oh, okay. That is the issue. So let me say this is then 4. And now when I'm substituting A4, I substituted by then 4. Okay, now it should work. So what I was trying to do is, I was trying to like have two variables of the same name, one with which was symbolic and another which had a number. So now if I double it out first, now this should work. Yeah. So now I get a homogeneous transform which has 0, 0, 0 and 1 in the last row, and then there is a 3 cross 1 uh, vector right here, which is going to show me the end effector position in the fixed frame. Now just let us just look at this values 2, 0.8 and 2.7, and let's see if we can actually see those on our diagram. So what the values that I was getting was 2 point something, let's say just 2.4. So these are the values of x, y and z of my end effector, x, y and z. 2.4, 0.9 approximately, and about 2.7. Now let me, like, I want you to visualize the robot and see if your answer is correct or not. So what we did was, now remember that initially our robot was at this home configuration, and what we did was we first displaced it by theta 1 by 20 degrees, so it would go like, so it would move in this direction about the base, so it would go into the plane a little bit by 20 degrees. Now theta 2 was 10 degrees, so instead of being this, it would, so my theta 2 was yeah, so my theta 2 was this, so positive 10 degrees would make this come here, so this would be 10 degrees, right? And then my theta 3 was 5 degrees, so my theta 3 is 5 degrees, so instead of being horizontal it would come here, so this would be my 5 degrees. And then my a4 was 3, and then my theta 5 was 30 degrees, so it would come down a bit. And then my theta 6 was minus 20 degrees. So I want you to give it some time and see if you can actually visualize it and see if you are getting the right answer. As far as I can see it, I think, yeah, the answer looks to be pretty right. Since there is a bit of a y, which is due to the fact that we are into the plane, which was due to the theta 1. And then there is x and z involved, both are positive, since it always, the end effector location is going to be right here, which is going to be above the x axis and in the positive z direction, right? Which makes sense. So I know that my XYZ that I'm getting are correct, and my these 3 cross 3 matrix shows me the orientation of the XYZ axis in the fixed frame. I know that this video turned out to be longer than I wanted and expected it to be, but I just wanted it to be a comprehensive video where I can show you how to do the forward kinematics and how to input it into Matlab and find out the answer. I hope you did not get too bored along the way, and this is all that there is to it, to doing the forward kinematics of a 6 degrees of freedom robot, and this is honestly as complex as a robot can be in real life. So I have shown you a very complex, like a 6 degree of freedom robot, and anything that you are going to encounter in real life is probably going to be equal in difficulty to this, in difficulty to this, or easier than this, so it shouldn't be a problem. And if you still have any queries or comments or any confusions, feel free to comment down below, and I'm going to make sure that I reply back to you in a reasonable amount of time. And if you like this video and you want to support this channel, don't forget to subscribe to the channel and share this video among your friends and let them know. And as always, see you in the next video. Thank you for watching.